All right, people. I think we're back on track. I just want to check here the stream, which I have on another device. You're not hearing double. That's me. Actually, it's way better. Wait, I think I solved it. Did we just solve OBS? Did we get rid of all of the troubles forever and ever? Wait, is this it? Wait, if I scroll really fast. Oh my god! I think we got rid of it. I think we solved it. We have conquered OBS. The holy grail of this channel was dominating and domesticating OBS. And I think I found the perfect settings. Look at that! Oh my god, yo, and if I move very fast in the camera, nothing's gonna change. Yo, and if I scroll at the same time, you can't see me. Oh, dude, wait. I am extremely happy now. Can you believe it? It's absolutely impossible. Like, what? Okay. Whoa. Okay. So now I know what the perfect settings are. Do you not want to know a secret? Do you want to know what the perfect settings were? It was ignoring whatever Twitch recommends. There was a little button that said something like enable enhanced broadcasting so that Twitch could sort of diagnose your stream and like tell you which settings to use. I simply disabled that and all the problems went away. I disabled that, I used my own settings, and now everything is working wonderfully. At least from my view. Let me know if you guys can see it as clearly as I'm seeing things. This is a new era in the channel. This is a new era in the channel, and it means we're going to have a very successful stream today. Yeah, that's all. Okay, so now I've verified that it looks decent. And that today is gonna be a great session. So give me a second, I need to store this thing. It's my work laptop from which I see the streams. All right. Let me get in the, in the professional programmer position. Sit down, relax. All right. Hello, everybody. Welcome once again to a stream from this channel, SharifSegfaults. And today we're going to be sort of continuing our work, and let me change to say hello, continuing our work with the memory allocator. Yesterday we were writing 3. We finished writing Malloc 2. Well, no, Malloc we finished the day before, but we ran some little tests on Malloc to see that it actually worked with the memory inspector, and it did, which is very surprising and something we're very happy about. And now we're going to proceed with the free function, right? Yeah, I mean, that's mainly it. So, I don't know. I'm really happy today because it seems like we figured out OBS. Seems like everything is fine, which is absolutely amazing. Like, it goes butter smooth. It's really cool. And yeah, that's all. So let's begin, I suppose. Yeah, so just to recap on what we've done, right? Yesterday, well, we have already coded all of these block member variables, which we've been really familiar with, the block family members too. We've been working with Malloc, right? And for Malloc, we usually need to modify blocks in some sort of way, especially partitioning them. So the partition block functions do exactly that, these two functions. And from the side of free, we need to coalesce blocks together, right? And that is what this simple function does. This function is only 2 lines long, but it's going to be a little bigger once we take a look at the logic behind realloc. This thing initializes our memory, but honestly, basically does nothing. Penguin Operator, welcome to the stream. Penguin, do you guys, Coding Barra, welcome. Do you see how buttery smooth the stream is? It's absolutely incredible. It's, hopefully it's the same on your end. I know that on my end, it looks very nice. It looks like decently smooth. Nothing is lagging. Because I discovered the perfect OBS settings. I don't know if you guys were here before when that happened, but look, like we can scroll super fast. Doesn't lag the stream. Can move also super fast, and that doesn't lag anything. So yeah, hopefully, hopefully you guys enjoy, because I had been very sad that the stream wasn't, you know, that it would lag all the time, and so we would have to go on these sort of tangents to simply just, try and fix OBS. Damian Rice, welcome to the chat for the first time. Hello. Let's see. And yeah, welcome. So, yes. You guys know each other? Whoa. Ganga Kamal 3, welcome to the chat, and welcome to the channel in general. It's good, guys, seeing you around. I haven't seen you before. No, it says it's your first time here. But yeah, so we're working yesterday on another channel. Oh, you guys met each other? Coding Barra and... Okay, that's interesting. But yeah, so welcome to this channel. Today we're coding a memory allocator. Well, not today, right? We've been on this sort of quest for some days, right? It hasn't been that much time because I had to take breaks in between of like 3 to 4 days of no streaming. But we're going strong and consistent. And yesterday, well, no, the day before yesterday, we implemented Malloc in what we called the Great Malloc Rewrite, because we detected some little mistakes in the logic with Malloc, so we decided to simply write it from scratch. How long are you streaming today? So hopefully I can stream until 10 a.m. My time, so 2 hours and 30 minutes from now. Perhaps, maybe we extend it until 11 a.m. So 3 hours and 30 minutes. The most likely one, 2:30 a.m. Okay. Sorry, not 2:30 a.m. 2:30, 2 hours, 30 minutes. Yeah. And potentially 3 hours, 30 minutes. Let me first check my calendar to make sure. Okay, I see. Yeah, so I think it's possible. We'll see. We'll take a look. But yeah, so welcome everybody. As I was saying before, we were writing Malloc before. We finished that implementation. We tested a little bit of it just sort of by taking a look at how the blocks behave, at what was going on. We could only take the branch that implied the last block not being free and the entirety of the thing being completely full. The reason for that is because we hadn't implemented free. Now that we have implemented free, the scenario changes, right? Everything changes because we're going to now be able to create all of these interactions and get into the actually very complicated part of our memory allocator, which is going to be sort of leveraging the advantage of the red-black tree and all of that. So it's gonna be, a little bit tedious. There's gonna be a lot of testing, a lot of taking a look at bytes in memory to see if they were set to the right thing. But before even starting all of that, we're going to start by testing free, because we hadn't done that before. So actually, I think I need to change the name of the stream. Testing free. There you go. Testing free. And potentially, I imagine we're going to and red black tree, right? So we're going to test both of those things. The red black tree we have already tested in our previous implementation, but it's always good to do that again. So yeah. So you may be asking, how do we test free? Well, very simple, right? The first thing we do is, well, of course, we initialize memory. We erase absolutely everything we've done so far. And what we're going to do is we can basically mimic the behavior we've been having with these previous allocations, to which we say, I don't know, copy some sort of information, like this, right? This is 23 bytes long. And then after that, we, for example, free that spot in memory, mm3, and then we free whatever A1 is. And after that, we allocate again the same type of thing. So this is just the test that we are able to indeed reuse the same blocks if they are able to suffice the user's request. So maybe we can make A1 be equal to Malloc again. And then this is 23 bytes long. Well, this is 23 and some, well, 23 characters. I think that is indeed 23 characters. No, 21. So then we add 1. And it's actually 22 characters, but 23 bytes, because the null terminator also counts. And once we've done that, we can free this again, right? I think it's better if we differentiate them. A2, A2, A2. And then we create a third allocation that is actually maybe, so let's see, 23 bytes would get aligned to something like 28. So if we have a block that's, or a request that is something like 27 bytes, we should be able to also satisfy that request. So if we now do A3 and then write something like, hello, this is 27 characters. I think that's indeed 27. Charles, and then a little happy face and then an exclamation mark. Yeah, so that's 26 characters, but then the null terminator, it's so instead of Charles, it should be bytes. And I think that's indeed 27. Yep, 26 characters plus the null terminator, 27. And finally, we free that spot. And for one last time, oh, Mariam, welcome to the channel and welcome to the chat. Yeah, today we are coding a memory allocator. We are testing our implementation of free because yesterday we finished doing that. This is indeed not hard to do. And we also tested Malloc for a little bit. So today, given that now we have both, we'll be able to test all of their interactions, which I suppose is going to be very, very catastrophic since, since it's very likely we have lots of bugs, but we will see. What can we include here? Something like this is once again 45 characters or something like that. I think that's indeed 45. 55. So we can just eliminate 1, 2, 3. I think that's it. 48 still. Okay, let's just make this 49. And then after that, we'll be able to free whatever this is, right? Free A4 and then return. And then we complete this. Okay? So So. Let's enter here, the terminal, and let's compile our program. I think we have the command over here because we've been using it quite often. De Ferrari, welcome to the stream. There's a lot of new people in chat. I remember you from yesterday because you followed yesterday, but it's your first time. Just don't free memory, and you won't have bugs with free memory. It's just, excellent advice. Yeah, those who use free are weak. Just reuse the same variables you've already allocated, and you'll be fine. But yeah, it is an interesting proposition. I'm not sure if we're gonna follow that because I want to get a job. Like, well, not a job. I don't want to get fired, but yeah. Incredible memory. I saw your YouTube yesterday. I've written a few pretty simple allocators. Oh, wait, excellent. You saw the YouTube. That's great. But yeah, excellent by the fact that you've written some, sort of all the allocators. That's pretty good. This is our first, well, I mean our as in the community, as in, or my first memory allocator. Never had done something like this before, but I guess that's the way you learn. And yeah, I don't know. Well, in the meantime, let's run this program and see what happens. So we're interested in seeing what happens at free. For now, I'm not gonna run the malloc tests. I'm just gonna run the free tests. This bar is annoying. In this terminal, we can make it a little smaller. All right, let's see. When we debug, what will happen? Place your bets now. Will it work? Will it not work? Okay. So, we enter the debugging phase. Perfect. So now we need to take a look at the memory inspector over here, memory. And I think you guys are able to see the kind of the camera is getting in the way. Oh, I can enable preview now. Oh, so that I can see what the stream looks like without getting an external device. Dude, the Twitch settings were completely messing everything up. Let me make the camera just like smaller, and I'll place it here while we debug. There you go. That's the perfect spot. Okay, awesome. So now, you can take a look at the memory inspector. And what we're going to do is we're going to add a new view. Well, first we're going to kill whatever we have here. We're going to add a new view to enter the heap that we have, which is 0x1234567106257C0. We want to look at 4 megabytes into the future, and here we are. So this is the beginning of our heap. Now we continue, and then we allocate 23 bytes. As hopefully all of you remember, we need to see something like FFFFFF over here representing the ghost node, and then we should see the hex for 23 after that happens. Yes, so FFFFFF. Then we enter the hex of 23, which I'm sure it's 1C. Is it 1C? Because 1 would be 6. Is it? Wait, am I tripping? No. This is indeed the correct thing that we want to see. Okay, perfect. And so now what we have is this 23 bytes long thing. We simply copy that message and we should be able to see it here. There you go. You can see it on the side. This is 23 bytes long, so everything is working. Our memory allocator is indeed giving us the correct thing. And now we're interested in seeing what happens when we freeze something, right? So remember, these first 4 are the size of the ghost node. These over here, these 4 bytes that follow are the root of the tree. Now, which block is the root of a red-black tree? For now, it's undefined, so we make it FFFFFF. After that, we have, the left, right, parent, and caller. Run LML2. Thank you for following. Yo, we have a new follower, guys. Let's go. Everybody, welcome Ron. But yeah, we have the left, then the right, then the parent, these 4 bytes. And after that, we need the footer, which is these last 4 bytes. Then starts the actual block. These first 4 bytes are the size, and then the rest are given to the user since we don't need the metadata when something's allocated, right? And so what we do after, if we need to free, is to simply change this 1C to become a free block. So this message will stay there, or it's supposed to stay there, because there's no real need to clean memory after it is freed. It is, internal to the process. There are no security issues. Instead, what we need to see is this byte over here changing to 2, if I remember correctly. It's either 2 or 1 to indicate that the previous block, meaning the last block, is free. Okay, so we should see the prev free become free. Let's enter into the function. So first, we calculate which block this belongs to. And this should be block number, let's see. So 1, 2, 3, all this is 16, 17, 18, 19, 20, 21, 22, 23, 24. So either 25 or, no, it should be 24. Yes, block 24, so it identified it correctly. After that, we need to assert that that block is not free, which is indeed the case. Yes. Now we set the size of the block. Ooh. What are we doing? Oh, we're reinstating the footer, but the footer has not been modified, so everything should stay the same. And now we set this block to be free. So we should see this byte change to 2. Yo, let's go. So we saw this byte change to 2, and you may be saying, oh, I saw this byte also change to 1D. Why? Well, the reason is because we're storing inside the header of our block, which would be all of these, 1, 2, 3, 4, inside of size, which is the as, we're storing whether the previous block is free and whether or not we ourselves are free. So we ourselves are free means that this last bit of the number became a 1. So it sort of transformed itself from a 1C to a 1D, which means that the bit was indeed changed. And the 2 over here is because the second to last bit changed to a 1. So now it previously was a 0, now it's a 2. Which means that, yes, the root says the previous block, which is the last block, is free, which is, this guy's free. And everything seems to be working fine. Fanbig asks, have you ever worked with Vulkan? No, I never, ever in my life. I have heard of Vulkan. I know it's sort of a competitor to OpenGL. It's not at all clear to me. Like, I never, ever worked with it. Is there a reason why you ask? Or like, are you working with Vulkan? Let's see, so now we can grab the next block of this thing, and there should be no next block. So next block should become the highest possible value for our UN32. Yes. Perfect. So now we know that the next block is a null heap pointer, which means we don't really care about it. So we skip this section. And now if the previous block is free, right, then we're going to also merge with it. Right now I'm software rendering my custom UI with Wayland, but I want to make it work with Vulkan, but I'm a bit scared based on what I've heard. Oh no! Wait, what have you heard about Vulkan? Is it like very scary? Because I've heard people praise it a lot and be like, oh, this is the future, OpenGL is outdated and all of that. So is there any reason why it's like, oh, hard and verbose? Okay, I see, I see, I see. But yeah, I don't know. Ooh. Mm, I'm sure you'll be fine. Just there's always one thing. There's only one principle that you need to have in mind. Throw yourself into the void and do it. Because if you trust yourself, you know that you'll have to get out of it eventually. Like, you know that you have to find a way out. So if you just try it out with informing yourself first, if you just go and try and implement it, you'll eventually find a way out. Like, but yeah, I mean, good luck with that, with the custom UI in Wayland. Um, you have an SDL2 implementation of my custom UI that works cross-platform, but it just doesn't have the performance that I'm looking for. This is why I'm making a more low-level implementation so I can have more control. I see, I see. Is that why you're using Vulkan? Once again, I have no idea about Vulkan, because once again, I have no experience with the world. Um, but I've heard Vulkan is like more performant and all of that. So is that the reason? Your problem is not does it work? Does it work well enough? I see. I see. I see. I see. I guess there's only one way to know it, right? Like, unless there's some other way. But yeah, um, I think the previous three should not be set, so we should be able to skip this. Yay! Okay, perfect. Then we need to reinsert into the red black tree, whatever this thing is, which means um actually no, we already set it to be free, which means that there's really no need to do this. Okay, Penguin Operator, we'll see you. We'll see you once you come back. But yeah, so there is really no need to do this. I think we can just delete this after we finished the debugging. But setting this to free shouldn't change anything. Yeah, indeed. Then reinserting into the red black tree. It looks so weird having a Windows 10 title bar on Linux, but I kind of dig it. Interesting. See, why did you decide to make it like a Windows 10 title bar? Like, are you a Windows 10 fan? It's just that, like, the performance is awful, but the interface is pretty good. I see, I see, I see. Yeah, no, that's reasonable. It's very reasonable. Dude, and I notice now that there's like basically no delay. There's like your response, it's like absolutely fast. It's nostalgic. I see, I see. Yeah, decent enough reason. Um, let's see if we. Okay, I'm trying to see if we insert into the red black tree, what is supposed to happen. So these four are the sides. We should see this guy, this FFFFFF, become 24, so as to point this block to be the root. Then we should see the left, right, and parent become null heap pointers. Something like, oh, there is absolutely nothing here. Let's see. Ooh, that's not ideal. Like, it is, but at the same time, it's not. So 18 is 24 in hex, so we're completely fine. That's great. It's what it's supposed to be. But here, we have that the parent, it should be nothing, but that doesn't end up being, sorry, the left should be nothing. But it may be able to use user data as the left. And then here, the right. So it's still using the user data that's there, and that should not be the case. And then over here, we have the parent. The thing is, with the parent and then the caller, we have another situation. So the caller was set correctly, if I remember right. So in our enum, we have that red is 0 and black is 1. So yes, the root of a red black tree should always be black, right? And for that reason, we should be okay with it. Windows 2000 was the best Windows. Changed my mind. Yeah, I have never used Windows 2000. I wasn't born back then, so I don't know. Oh, funny like that. So you're also pretty young. Interesting. Yeah. Yeah, we have a problem. We have a problem. We have a bug. 2005, sir. Damn! 2005? Absolutely incredible. I'm 2006, so we're basically the same. Absolute. Whoa, that's amazing, dude. And you're already creating a wait, no, what? Your own custom UI? What? Damn, that's crazy. Wow. Um, how come not owning like? I mean, there is well, hi Shmeliok. Okay. Welcome to the chat for the first time. Um, I mean, I've heard of Odin. I've heard of Odin. I don't. I honestly, I have no experience in Odin. It's one of those things that I want to try, but I would like to try it after I try Zig and after I try Rust. So it's still a little bit far into the future. I died to make something in C++. Yeah, so usually I code in C++. This time we're coding in C. It's my first serious introduction to C. Um, when you say I died to make something in C++, do you mean like I would die if I had the chance to make something in C++? As in like it's incredible, or as in I would die if I were to do something in C++, as in like it's the worst thing ever. Rust mentioned, indeed. I've heard of Rust a lot. I want to learn Rust, so eventually we'll do something like that in the streams. You seen Bun moved from Zig to Rust? Yeah. I saw the polemic rewrite that initially was allegedly a toy experiment and then it ended up becoming an actual thing. Um, yeah. Seen it. I remember seeing the news of the rewrite, but yeah. I assume that from the message you are a Rust fan rather than a Zig fan. Yeah, that's true. But in the meantime, as you guys respond, we're going to have to fix some issues. And the first issue is that the red black tree, whenever it has a new node, it it needs to sort of put in the parameters that it's supposed to. What do I mean by that? What I mean by that is we need to assert that the block is free, but we also need to sort of, starting metadata. So this node should have a left, right? So set the left on my block, which should be the new node, on the new node, to be a null heap pointer. So this has no left child. This also has no right child. And it also doesn't have a parent. Set parent of the new node to be a null heap pointer. Okay? Because currently, as the memory inspector states, we are not replacing the user information for those fields, which means that we are using, like, this is just security vulnerability, or not security vulnerability, just some sort of, well, it is a security vulnerability because somebody that's smart enough to realize that this is a bug could just introduce the right to left and right, things and make the program crash or something like that. And so it's better if we just do things this way. Left, right, and parent. Yeah, what else do we need to set? I think nothing else because the color is set later, I would assume. But just to be safe, we just set the color at the beginning to always be red. Because remember, when we insert into a red black tree, the color is always red. ZM, welcome. Oh no, did Ross Evangelist find the stream? Mm, so we have the first Rust opponent. Have you tested alloc free yet? That's exactly what we're doing. So we're testing, or we're trying to see sort of a first toy example. Now that yesterday we implemented free, so this toy example is going to be treating like, first allocate 23, free that, allocate 23 again, which we expect to use the same block. Then we free that, allocate something that's slightly bigger that still fits in the in that block that you have allocated because of the alignment. So we should be using that first block still, then free that, and then allocate something that's bigger than the block that's currently available and see that the heap expands to merge with the block that's currently free. So we're exercising those paths. We're just a very minimal toy example to see that everything is working well. After we see that, like, it seems like it's working well, we start writing, crazier tests where we actually take a look at everything. Cobalt Ethon, welcome to the chat. And hey yo, yeah, hey yo to you too. Yeah. Whoa. You're just dropped. Let's see. Is this a Ross defense? Are we seeing a Ross battle being formed in the chat? Rust is too much for me. I just want to make games, not spend 6 months learning the crazy borrow checker in Rust. I heard people spend 6 months up to 1.5 years just to fully wrap their heads around lifetimes and ownership. It's too much. Fair argument. I cannot say anything because, once again, have not tried Rust. I do know of the concept of, like, the theory behind Rust, the barrow checker and, like, lifetimes, etc. But never coded on it. Well, I've coded like once on a little program. Valid opinion. Maybe somebody has a different opinion. We'll see. but yeah. So that is the sort of test that we have currently. And right now we are detecting bugs. So one of the bugs is that in our free function, whenever we free the block, which is over here, we never really change the metadata related to the left, right, and parent nodes because we were assuming that the red black tree would do this, and in fact it didn't. And so what it would do is it would insert the block, but not change those fields. So whatever the user put here would still remain as like the left child and the right child and all of that, which is of course a security vulnerability. And not only that, completely unintended behavior because once you enter this first block, which would be the root, you would go down the tree by following pointers that are not even like correct, right? I've just never learned lifetimes, so I just do what compiler tells me, and if it doesn't work, I cry and abandon the project. So far, it's been a success. You could call me a lifetime impressionist. All right. Also, fighting the borrow checker and wrestling with lifetime annotations. Prime A everywhere. Yeah, I imagine it may be annoying. I feel like you feel the pain once you do it yourself. So that's what I want to try out. And yeah, we'll see. We'll see. Um. So, okay, we've introduced these fixes. So now the metadata should not get corrupted by whatever the user has been doing. And I think, yeah, I feel this is reasonable enough. Let's recompile and let's debug again. So here we have the heap, and now we need to open a new view in our memory inspector to take a look at the heap. So the heap is now a different thing, which is 0x1234567100595 740. Perfect. We want to look 4 megabytes into the future. Also, if I don't know about sugar. Oh, wait, no, this message already was there. Welcome to all of the new viewers that we're having. Currently, we're writing the memory allocator. we're writing free. Actually, no, we finished writing free and now we're testing it. We're seeing if it works. So we're looking at the individual bytes to see if everything is being set, if everything is in the right place, things are working okay. So yeah. Over here, I think we initialize the heap, which is fine. Then we test free, which is what we're interested in. We initialize memory. And after the first allocation, we should see the FFF and then 1C. Yes, okay, so this means there is no root yet. Then this, whoa, there is no root yet? That is strange. That should not be the case, actually, now that I think about it, right? Am I? Oh, no, 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 no. That makes a lot of sense. There is no root because there is no free block, right? So a red-black tree has no elements. So there is no root. And then 1C represents the 28th, I think. What's the 1C? C is 12 and then 16. So 12 plus 6 is 28. Okay, 28 by block. When we write the message, we should be able to see it, and indeed we see it. This is 23 bytes long, which means our memory allocator is working as usual. Then we free it. So let's see what happens on free. On free, we should see the block be block 24, because that's the heap pointed to the first position of the block. Then after that, we should set the size again to reinstate it if the user overrode it with whatever they were doing. In this case, no, because there's still a 1C over here. So we should see no change. Perfect. Now we set this block as free. That means that this guy is going to change to 2, as we saw before, and that this guy should set to 1D. Yes. So the 2 indicates that the second to last bit is being set to 1, which means the previous block is free. And this 1D means that the 1C had its least significant bit changed to 1, which means it's now like 1 more, and means that the block is free, because that last bit is the one that marks whether or not it's free. If we continue, we see that there is no next block because there's only one block, and so next block is just undefined, or a null heap pointer, which is represented by the max value of a uint32. And that means that we're going to skip this branch because there is no such thing as next block. And there is also no such thing as a left block or a previous block because we only have one, which is the current one we're looking at. So we don't need to coalesce with anyone. After that, we set this to free, which we already have. And then after this, we make the arbitrary insertion. And what we should see is the following. Okay, we should see the size over here, which is fine. Why is your null a uint max? Oh, so our null is not 0, right? So we declared this variable called null heap pointer. This is like our own. We're not using the C null. The reason for that is because in the 0th address, we have a node that we call a ghost node, right? It's called a ghost node so that it points us in the direction of where the root is. Since the tree is going to be constantly rotating, the root is going to change all the time. So if we save a pointer to the root, it's very likely that a rotation, it's going to change the tree so that whatever node we're pointing at is no longer the root. So what we do is we create a node that's just useless. It's just, well, not useless, but it just is not involved in the tree at all. So we just point at it. So when a rotation happens, the rotation is interpreted as a subtree rotation. And then the ghost node gets immediately updated since it's believed to be a parent. So the ghost node is always be pointing at the root of the red-black tree, which is this field over here. And that's why you see it as FFFFF, because there is no root. If this were to be 0, it would make us go over here, and then like, you know, we would be touching a node that is completely bogus and it's not supposed to be there. 0 is like not a valid value because you should never interact with the ghost node. It's just a value that is valid for us because we need to reference the ghost node, but the tree shouldn't be able to reference the ghost node, right? So we still want to interact with the ghost node because like it's gonna keep track of the state of the tree and like, you know, all of this stuff. We just don't want the tree to take a look at it. So and since our blocks are at least 20 bytes and we're guaranteed that our heap is 2 to the 32 bits long, 2 to 32 bits long, it means that it is impossible for the uint max to be an actual node pointer or a block pointer, right? So this is an actual invalid value. This should never be the case that it represents a block pointer. So yeah, that's the reason why. And over here, when we insert into the red-black tree, we should be seeing that things change. So we enter this function, we assert that the block is free, which indeed it should be. And then we set the left to null, the right to null, the parent to null, and then we set the color to red, which should make this an FE. Yes, okay, FE. Perfect. And then after that, we continue with the whole thing. This is the red-black tree insert, which we tested in our previous implementation. We need to test whether or not the translation we did is correct, which is a little bit scary. It detects that this is the root of the tree because it's the only, you know, the red-black tree was empty before. So this insertion will represent the root. And so it links it with the ghost node. Perfect. The ghost node is now pointing at block 24, or like block with block pointer 24, which is indeed the case. This is position 24. And then it's going to set the color to be black. So it should, the parent is 0, pointing at the ghost node. And then it sets it to 1 because it's black. Yeah, perfect. So now we return. And when we return, we have a valid state for a red-black tree. Perfect. And so now when we free this, nothing should happen. Great. So we have one free block that's 28 bytes long. 28. That means when we perform this new allocation, we should see this guy. So we should be seeing, let me align them. We should be seeing 100595750 and then 1D on top of that. So 76D. And we should be seeing it in A2. Ooh, 75C. Is that the intended? Is that a problem? Well, am I just not good with hex? Oh wait, no, you don't add a 1C. You add 8 to it. So you should be seeing 5758. 5758. Oh no, never mind. Because we don't give the user the block pointer because these first 4 bytes represent the size. So we should be giving the user this direction, which is indeed C. So 7, 5, and then C. Yeah. Oh, we gave the user the correct one, which is amazing. It means that our red-black tree is working. And then after that, we write into it, this is 22 characters, and then the exclamation mark and everything. It is indeed in the correct position it should be. It overrode all the metadata. And when we free it, we should see the metadata change again. Perfect. Yay. Okay. Coding Barra asks, what mic are you using? I don't have a dedicated mic. I have these earbuds, and that's what I use. Yeah. Is it sounding bad? Or is it If it's sounding bad, then we can change to something else. But yeah, let me know. Let me know. It's audible. um, by audible, you mean like, you know, yeah, I can hear you, but it's total trash. Or like, it's decent enough. It could be better, right? Is that what you meant? What you mean? It could be better. Oh, it's good. Okay, that's good. That's good. Um, yeah. So over here, we're gonna perform another allocation. This time a 27-byte allocation. And you may be saying, is the best sounding earbud mic I've ever heard. Well, these are like the Apple ones. The what's their name? AirPods. AirPods. Yeah, this was a gift I got, and so I use them now for streaming. So yeah, um, free 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 ad for Apple, I suppose. I don't know, but yeah, don't really like the Apple products because they enclose you in the ecosystem and all of that. But the AirPods are very good, you know. Anyways, we have so now we're gonna allocate a 27 by block. And the reason why this is important is because it's more than 23, but notice that the block is actually 28 bytes long because of the alignment that we needed to perform. So despite the user not knowing, we're going to use the same block as before. We should see that happening. If we see the heap expanding, that is a problem because it means we're not taking advantage of performance or the blocks that we already have. So let's see. We allocate 27 and we should see this 1D change to whatever 27 is. Sorry, 28 because it's still a 28 byte block. Yes. Okay, perfect. And when we write the message, we should see this 1C basically disappear. The only one that should stay 0 should be this guy because it's going to be the null terminator. And then this guy because we never touch it. Yes, perfect. So we see, hello, this is 27 bytes, happy face, exclamation mark. Great. So we're reusing the same block. And when we free it, we should see the size come back. So 0, and then 1C. And the rest be a bunch of Fs. Yes. So F, except for the parent, which is 0, since it points at the ghost node, and 1 because the root is black, and 1C is 0, because that's the size of the block. So this is indeed the correct thing. Now comes the most difficult sort of thing. We've never tested this path on Malloc. So let's pay attention to it. We're going to allocate a 49 byte request. So when we enter Malloc, we know that this is not the first call, so lazy initialization should be skipped. Yes. Now, 49 is not 8 byte aligned. We're going to align it so that the block in its entirety, that is the user section plus the size, is actually 8 byte aligned. And that implies that the size of the blocks needs to be 52. Right? You may be saying, sure, but 52 is not, a multiple of 8. The reason for that is that 52, which is the user section, plus the 4 bytes we use to represent the size is going to be 56, which is an actual multiple of 8. Now we continue. We try and find a free block in our red black tree. And this search should return null heap pointer. Why? Because although we have a block that's free, which is the previous block we have been using, the 28 byte long one, it is not enough to accommodate for 52. And indeed, we get a null heap pointer, which is the UN32 max. So now we skip this entire section and we realize, oh, we need to expand the heap, right? We calculate the expansion size. So either we expand by the expansion factor times the heap size. The expansion factor is currently 0.35. So we expand that by 35% of the heap, which is just some arbitrary number. We haven't really tested what number makes it efficient. And I think yeah, if I just make this a little bit smaller, you guys will be able to see. Yeah, I think that's perfect. Okay, so what we do is we take the maximum between the expansion factor in the heap, the minimum amount of, or sort of the exact size of the block that the block needs, and then the minimum size a block could ever have, which is 20. So here we're dealing with the size of the heap, which I think it's just 28, right? Sorry, no, it's 32. 32. 32 times 0.35. So we add 35% more to 32. That is not enough because this number here is 52, so it's winning. And this one is 20. So this expansion size should expand by 52. Or sorry, by 56, actually. And indeed, expansion size is 56. And so what we do now is we're going to, let me shrink this a little more. You guys can see the code. Or actually, let me just, sorry. I'm gonna move the camera a little. There you go. Perfect. Perfect. Okay. So what we're going to do next is we're going to. Oh wait. Oh, sorry. I thought the camera was frozen. We take a look at whether or not the last block is free. Now remember, we only have one block so far, and that's the block we just freed from the previous allocation. So the answer should be yes. This should be true. True. Then we try and find, if it is indeed free, we try and find what block that is. So it visits the last block size. It should see the 1C and then travel back enough to discover that, yeah, the last block size is 28. And then point to the last block, which would be 24. There you go. So the last block is indeed the block in position 24. And then from the expansion size, we can reuse the space that this block is already using. So that should be expansion size minus the 32 bytes that are being used by this free block, which we can just simply, recycle. And so what we do is we simply say, well, expansion size 56 changes to 24. And we're going to then remove this from the red-black tree. Remove who? Well, we just remove the block that's free. The only one block we have, because what we're going to do is we're going to expand the heap. Mem heap size should now change to, why is it 56? Oh no, yeah, it should be 56 because the ghost node occupies space plus the space that's being occupied by the little guy, the first block we allocated. Then after this, it should be expanded by 24. So you should get to 80. Perfect. There is something nonetheless that we have to note. Notice that the last block being free is something that actually accounts or like should be taken into account for this calculation. So like we are making it seem that we need to expand the heap by this much. But actually we don't, right? We don't really have to, because as you can see, we actually need to expand it by 24. So like it's after the fact that we calculate the expansion that we subtract the things that we can reuse. I think it should be the other way around. We subtract what we can reuse and then calculate if that's enough, or like and calculate the expansion size, because it's probable that the expansion factor is greater than 24, just not big enough like 56, right? And for that reason, I think the calculation should be done backwards. So let me simply write, well, I guess I cannot write, I don't want to write it here since we're debugging and that may change the placement of the lines. Let me see if that changes the placement of the lines. To do perform calculation of recyclable space before expansion size. Perfect. And so what we're going to do is, ignoring that, which is a very minor detail, we know that the last block is indeed free. So we're going to make that last block be the size of the new area plus whatever it had before. So the last block had size 28 plus the 24 that the expansion size gave it should be the whatever that is, which is 52, right? So we go in. Last block is free, yes. Then we enter and we should set the size. Yes. So the size now, it says it's 35. 35. 35 in hex would be 3 times 6, 18, 48, and then 48 plus 5, which is, 53. Oh, but that's because the last bit is set, because this is a free block. So 34 is the actual number. We are fine. This is indeed what should happen. What we do now is we take a look at that block, and we see if it's worthy of partitioning. It should not be, because the block is basically exactly the size that the user needs it to be. So we continue. Perfect. And then we return that to the user. And then the user should be able to allocate whatever they need. Perfect. So we get to 49 byte, 50, 51, and 52. Yes. Okay. Okay. This is, this is perfect. I think it's working correctly, right? This is once again 45 characters or something, right? Yeah, wait, no, this is the actual intended behavior, and then we return true. Oh, shoot, what happened? Oh, no, wait. When we tried to free it, something happened. Oh, no. Wait. Okay, what is going on? Are we freeing the right thing? Yes, we are. Okay, let's run the program again. Just let's skip to the part where the seg fault happens. There's a reason why this channel is named that. So let's see. What is the problem? Whenever we free, we pass a pointer. And we need to know out of the blocks, which block pointer does that normal pointer represent? So what we do is we take a look at the pointer, and then we subtract from it the size, right? We subtract from it the size of a unit 32T, which should put us in the first byte of that thing. So I'm not sure why this is returning something not intended. Because mem heap low, is there something wrong? Let's see. If we have, the char star pointer, and then we subtract from the size of our unit 32T, we're going to have the original pointer minus, So we have the 571758, which is what it's supposed to be, right? Which is 75 and then 8 should be this position, right? This position over here. It is indeed the correct one. And then we convert that to a uint pointer. Is that the problem? Uint pointer T. It shouldn't be, because it is 32 bits. Uint pointer is like 64. So we shouldn't worry about it. Oh. Okay. So, well, this still shouldn't be a problem, right? Because even though we convert this to a pointer, we subtract from it the mem heap low. And the mem heap low, when converted to a uint 32 pointer, to a uint pointer, should be a very big number too. Yeah. So 64904, 64. So all of this is in. So it's the difference between 904 and 880, which should be the 24 that this block it actually is. And that is indeed the case, right? So now if I just do this expression, which should be the uint pointer t of my char star pointer minus the size of the uint 32t, right? Minus the heap low converted to a uint pointer, we should be seeing 24. Yeah. So what's the matter? What's going on here? It says there is a seg fault, but why would there be a seg fault? Everything is the way it's supposed to be. Oh, actually, wait. That was not necessarily a seg fault, right? That was a sig part. Is the assert the one that's failing? I think it might be. Let's try it out. Recompile, reset, and run. So we continue, whatever, da-da-da-da. We go here, we free for the first time, we free for the second time, we free for the third time, and now we free for the fourth. And in the fourth time, this should not fail at all. And then we assert whether or not that block is free. And I think that's where the issue lies. So I think that despite giving that block to the user, we didn't set it to be allocated. We forgot to say, set this block to be allocated. And so the block is still free. Let's see. So when we malloc, we perform a lazy allocation, that initialization, that's fine. When we find a block, we set it to be false when it comes to its freeness. So this is completely fine. But later, if the block was a product of an expansion, we never set it to be allocated. Ooh, okay. I see. So here what we're going to do is, before giving this block to the user, we need to set its freeness to false. There you go. Okay, new bug discovered. We were not setting the block to allocated when the block was a product of an expansion, which is very concerning. Yeah, perfect. Okay. Actually, because we do it at the beginning, no? No, we don't. Ooh. Okay, that's concerning. Perfect. So this doesn't really need to be there. Perfect. So now, if we recompile, we should be able to see no assertion fail, right? Let's open it. We enter here, we initialize memory. This is the first free, the second free, the third free. This is the fourth free. So now if we go forward, this assertion should not fail. Perfect. And then everything should continue as usual. Let me just inspect the memory to make sure that everything is going well. So this is 0x1234567100061D 740. Yes, okay. So now we're taking a look at this block, which is the 34 block. We set its size, which means that these last bytes are going to become, there's 34, right? 34. And then after that, we set it to be free, so this should become a 35. And then this guy should become a 2. Yes. The next block, there is no next block. We skip this section. The previous one is not free because we are the only block. Then we set ourselves to be free, which we already did. And then we insert ourselves into the red black tree, which should make a bunch of Fs and then a 1. There you go. So F, 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 and then a 1. And then the rest of the user data stays because we don't care about it. It doesn't interfere with the metadata. So now if we continue, we should be able to return. Perfect. Okay, yo, our first test. Our first test for free and Malloc has officially, and it ended successfully. So that's great. That's great. You good? All right, celebration, yay. Okay, so we now know that the current version of free that we have and the current version of Malloc that we have are sort of worthy candidates. They're like decent enough to the point that we can think of introducing more tests. You know, we have faith in them. I mean, they're like, oh, I believe this guy works. So let's introduce a little bit more tests. So we are going to, maybe this is free. Then what is this? This is like one block. Well, test free 1. Okay, let's just call it that. Let's create another one. Maybe test free 2. And in this one, we're going to be a little bit crazier. So we want a pointer. We're gonna malloc. Sorry, no malloc. Nalloc. We're gonna nalloc. How many? Say 100. No, I was gonna say 165 bytes. Yeah. I mean, sure, why not? The only thing is like, ooh, I want to keep things like what's the name? Small, so that we can take a good look at it in the memory inspector. But let's do this. Let's allocate 3 blocks at the beginning. Char.p2 was nalloc 20, say 32 bytes now. And then char.p3 with a nalloc of 50 bytes, right? We're going to write stuff in each. So in P1 we write something like 24 bytes, and then however many A's are needed to complete 24. That's 30, 29, 28, 27, 26, 25, 24, 23 because the null terminator is a thing. So these should be 23. Yeah, perfect. And then we do the same for the other 2. We simply make this be 2, and this one be 3. And then, oh, sorry. And then this guy should be 32 bytes long. 24, right. 25, 26, 27, 28, 29, 30, 31, and 32. Perfect. And then this guy should be 50. So we grab the 32, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 42. And then 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now this is the 50 bytes. What we're going to do after is we're going to, okay, so let's test the coalescing of blocks. Coalescing. So we're going to first, let's do coalesce right. So we're going to free P3, and after that we're going to free P2. So P3 and P2 should merge together. They should coalesce to make a huge block that's like 82 bytes long or whatever the 8-byte alignment version of that is. And then once that has taken place, we should be able to see that huge free block. So now if we try and allocate, right, we try and malloc 82 bytes, it should use the big block. It should not expand the heap. After those 82 bytes are there, we now want to sort of test coalescing on the left, which means that if we now free the P1 and then we free P4, P4, once it's freed, it should see that P1, which is its left neighbor, has just been freed and thus merged with P1, which should give us not only an 82 byte long block, but a 106 long block. A little bit more because of the 8-byte alignment stuff, but you know, you get the point. So then if we perform a char P5 to be equal to malloc of 106, we should be able to suffice that request, right? Without expanding the heap. So let's take a look at that. After that, if I free P5, it means that our entire heap is empty. And then what we're going to do is coalesce both at the same time. So if I reuse P1 and then malloc with it the same, right? 24, then P2, and then we malloc with it 48, and then P3, and then we malloc with it 12, right? What we should see right now is 24 plus 48. Yeah, this is not bigger than 106, which means that we don't yet expand the heap. And then if we free them in the following order, if we free P3, right, P3 is going to take a look at its left and see that P2 is not free, so it's not going to merge. Then we free P1. P1 is going to take a look at its right and see that P2 is not yet deallocated, and so it's not going to merge with anyone because it has no other neighbors. And finally, P2 gets freed, and he should be able to see that P3 has been freed, P1 has been freed, and thus it should merge with both. So it would bring back the 106 long block, right? Yeah, so when we free P3, actually I was lying, when we free P3, P3 should see that to its right, there's a bunch of empty space, since we haven't used the whole 106 bytes that we got from here. P3 should see that there's a bunch of free space and merge with that free space. P1 gets freed, it sees that it has no neighbors that are free, and thus it merged with nothing. And P2 will come back to being free and see that P1 is free and P3 are free and merge with both. So that's the behavior we expect. And we're going to take a look at the memory inspector for that and finally return true. After this experiment, it will be nice if we are able to create some sort of testing framework by which we can specify how we want the heap to look, so that the tests can be automatic, right? Because currently what we're doing is we're sort of having a feel of whether or not the function is correct. It's not like we can run this test and let the computer tell us whether things are right or wrong. Currently what we're doing is just taking a look at it by ourselves and saying, yes, this is indeed the correct thing. Test free is not declared. Oh yeah, of course, because we need to run test free too. Perfect. So let's begin over here. And of course, we need to initialize the malloc module before even thinking of it. So reset, and then let's run this. Okay. we have the initial heap, blah, blah, blah. We continue. Okay. Now, P1, right? P1, I'm going to delete these variables that are unused. Perfect. P1 should, well, first of all, we need to go to the memory tab and take a look at the heap. So let me delete this view, let's add a new one, and then do 0x 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 5, B9, AA0. 4 megabytes into the future. Perfect. So this should all be 0. Once that first allocation starts, we know what it looks like, FFFFF1C. The second allocation should give us a new block that starts, I think, here, and that has as size, it should have 36, I want to say. And that is indeed the case, 36. Okay, perfect. And then we should see a block that starts here that has something like 52. Yeah, 34 in hex is 52. All of them are empty. So now we write on the first 24 bytes. Perfect, awesome. Yes. Then we write on the next 32 bytes. Perfect. And then we write on 50 bytes. Yes. Incredible. Okay. Now we free P3. And so P3 being the last one, we should see this 35, I think. Sorry, this 34 change to a 35. And this 0 change to a 2. Oh, what happened? Oh, I introduced breakpoints here. Yeah, I don't want that. Yes, 35 and then a 2. And then all of the metadata is reinstated, which is what we want. Perfect. P3 is now the only free block, so it should have a black root. Now we free P2. P2 it starts over here, so this 24 should become a 25, if I remember correctly. And this 35 should become like a 38, a 37. Oh, yeah. No, 35 plus 2 is 37, not 38. Sorry. Perfect. Now, this thing over here, this 5D is just completely wrong, right? 5D in hex is like a huge number compared to what we have right now. No? Yeah, why do we have 5D? It should still be 20. Yeah, there's something fishy going on. Something weird. Because 5D is a huge number. Previously, this thing was 24, as evidenced by the footer being 24. We set it to freeze, so now it should be 25. And then after that 25, we know that its previous, which should be the root of the tree, is not free and so that should still be 0. Oh, sorry. It just need. Okay. What may be going on? Because, okay, let's see. If we continue through the heap, right, we get to P1, get to P3. Sorry, I think we need to look at a new address in memory, which is 0x 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 6, 4, 5, AA 0. 4 megabytes into the future. Perfect, 24. And then after this, we should see a 34. Yes, here. Perfect. Then once we go through the step, we should see letters. Yes. We free this guy, this 35 something, and then it should become 34 should become a 35, and the guy on the top should become a 2. Yes, perfect. Right, 35. Everything seems to be correct. And then we free P2. So pay attention to P2. P2 starts here. Right, so it's a 24. Whenever we free it, right, we should see... Wait, I think you missed that freeing P2 triggered a coalesce right with the already free P3. Oh yeah, P3 is free, so now we coalesce it with the other one. And that should be fine. Yes, you're completely right. So 5D, yeah, multiplied by 16 is something around the 80s range. Ooh, okay, yes, no, that makes total sense. 5D is indeed the correct one, right? Because, yes, you're totally right. Yeah, the coalesce. I missed the coalesce completely. I'm so sorry. Yeah, so now that the coalesce, this single block should be at least 82 bytes long. Yeah, so now we should see this block hosting whatever the P4 is. So P4 should become the block address that's over here, which is block number, so 16, 32, 15, sorry, no, 16, 32, and then 32 plus 16, 48. It should be something like 48, 40, whoa, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so it should be 48, 49, 50, 51, 52, 53, 54, 55, 56. Okay, this should be block 56. So P4 should be given block 56. And, okay, so it should be given this, which is 645 AD in the C section, which is correct. Since we skipped the size header, we have the C. Perfect. So P4 was awarded the right block, means the red black tree is working correctly. Then we free P1. P4 is not yet free, but we free P1. And after that, and thank you so much, Bailey Bees, by the way. I forgot to say thank you. It's pretty good that your first message in chat was so helpful. Welcome to the stream. And oh, thank you, Sarvesh Cereal. I don't know how to pronounce it, but thank you very much for following. Yay. But yeah, so once we free P1, and it's gonna be free, right? The red black tree has as root the only free node we have so far, which is P1. Once we free P4, the root of the red black tree should be the same. It's just that this 1D now changes to something huge. Yes, perfect. 7D, and indeed the last block is free. Then we allocate P5, which we have a block for it, right? Which would be this huge block. So we should see the heap not expand by anything. Yes, we give to the user inside of P5 the 645AB, and then the C position, which is indeed correct. Perfect. Then after that, we free P5, and indeed, look that the red black tree has no root anymore since there are no free blocks. Once we free P5, we should see the root be 18. Yes, and then this guy gets freed. Now we allocate P1, and now P1 should occupy the space, the 7D, with 1C, if I remember correctly. And then after this, and then over here, we should see now the sort of remaining free section. So let's see. Yes, 1C and then 5D, which is the size of the remaining. Well, 5C actually. It's just that the least significant bit means that this guy is free. Then we allocate 48, which should it should change this value, but there is still free space. Yeah, 34. Perfect, 34, 34. And then this 25 should represent the amount of space left. But it seems to me that... Oh yeah, this is the only free node, right? So it has no left, no right, no nothing. It is black because it is the root of a red-black tree. Yeah, we're fine, we're fine. And so now we allocate 12. Ooh. We have an assertion failed. So, oh, okay. I see where it is. So when we perform a partition of a block, we determined that the partition is only to be made if the size that's needed is greater or equal to 20, because you need at least 20 bytes to store the metadata information, right? It's actually 16 bytes, right? Because the size of the block is size of the block is the first 4 bytes are already not included. So size needed only refers to the user section, and part of the user section we need it to be at least 16 bytes, so that when the user frees it, the minimum amount of metadata can fit. So partition block can only be called if size needed is greater or equal to 16, which I think we're not accounting for. Let me see. So the total space is this much. Total left space should be this thing plus the size needed, yes. Then the total right space, yes. So we also check that at the end, whatever we leave behind is or has enough space to also host the block. So where are we calling partition block with something that is not the size it's supposed to? Okay, we partition of worth it, and then we say if the block space minus the total left space is equal to the size of UN32T plus the size needed, then we proceed. Okay, I see. Well, there is something then that I don't really understand. Yeah, we need to make this size needed instead of being just whatever the user provides, right? We need to make it the max between whatever the user wants, the user being us, the programmers, whatever we want to partition this by, and the minimum 20 bytes that a block must have. I think. So I know it's a little bit confusing right now. Basically, I think let's go to the Excalibur for like a solid second. What's going on right now is this, right? We have our block in memory. Notice that I think this is not a correct drawing. I think this is a better drawing. Our current memory blocks look like this, right? We store the size, we store the left child, the right child, the parent, the color, then the extra amount of memory that you need in order to accommodate the user's request, and then the size. Notice that all of this metadata, all of these guys, are needed only when the block is free. Because only when the block is free does it live in the red-black tree. If it's allocated, it doesn't live in the red-black tree, and so this information is just useless to us. For that reason, we give to the user a pointer to this section of memory. So they're allowed to overwrite all of this metadata just because it's useless to us, right? Including the footer. And so what we're left with is just size plus whatever this is, right? The thing is, when we free the block back, we do need to store this metadata, right? And it means thus that the minimum amount that we can provide to the user is enough to hold these values and this value. each of them is 4 bytes long. So 1, 2, 3. The caller coexists with the parent through a bit field, so we don't count it. And then 4. And 4 times 4, given that each is 4 bytes, that's 16 bytes. So we need every block that's provided to the user to be at least 16 bytes, so that when the user frees it, the metadata to represent the free block still fits. So that's why that assert was over there. Previously, it was 20 bytes. It's just that after some optimizations, we managed to get it down to 16, being the minimum requirement. So yeah, that's the reason. I'm gonna delete this. Perfect. Okay. So given that explanation, this is what we're trying to look at. So we're taking a look at, partition the block. We can only partition a block whenever the left side is guaranteed to be 16 and the right side is guaranteed to be able to host 16 too. So yeah, that's totally fine. And then in partition of worth it, we need to say, well, consider worthy of partitioning if the size needed is between 16 and these guys. I think, yeah. So it's the max between whatever you actually need, considering alignment and all of that stuff, and 16, right? So yeah, the size you're gonna need is basically the max between the size you actually need and 16. Yeah, we don't need to make it more complicated than that. Yeah, so this size needs to be aligned to whatever we have. So I'm just gonna perform the same sort of motion, because 16 plus the 4 bytes that are used by the size is gonna be 20, but 20 is not 8-byte aligned. So this thing should be actually, this thing should be 20, and that's why I had a 20 over there. So let me just do size of uint 32t plus 16. Actually, I think I can just do this. I'm not sure why I'm complicating the code so much. It should not be that complicated. We just simply say, whatever size you need needs to be at least 16. There you go. And then we perform the alignment calculations later, just assuming that the size is 16. Perfect. That sounds about right. Size of uint32t plus 16. Then we consider worth it. If not, then we are good to go. Okay, perfect. Then I need to change this assert. If the size, assert that the size that you need is actually greater or equal to 16. Yes. So that should be here. Perfect. Okay. Now assert, the total row space, da. Okay. Yeah, this sounds about right. So let's recompile this. That's the reason why we had that assertion. And let's just rerun it. So let's debug. Then we go to memory inspector. We're going to take a look at where the heap is. So the heap is at this address, 0x1234567 1005 A97C0, 4 megabytes. Perfect. Then we continue until we get to the point we care about, P1. So allocate P1, P2, P3, we write the information we want. We already went through this. With free P3, with free P2, they coalesce, which is the 5D. Then we allocate P4, which indeed makes it non-free. Then we coalesce, we try and exercise the coalesce left. So we have 2 blocks right now. We free P1, and then we free P4, which should make this thing over here be really huge. Yes. And after that, we free the entire thing. So we allocate the entire thing first, 7C, and then we free it again. That's 7D. Yes, perfect. Now we allocate P1, it should be 24, and thus this 7D should change to 18, or well, it should change to whatever 28, which is the 8-byte line size is, 1C, yeah. And the free section is now 5D long. Then we allocate 48, so we should see 48 replace 5D, and then the 5D sort of move further down, right now to 25. And finally, we allocate 12. So this block of size 25 should be, let's see, is it enough for allocating 12? So 12, which gets converted into 16. 16 plus 4, 20. Okay, so 24 bytes should make it over here to the end. And then another 24 bytes. Yeah, it is like the exact size it needs to be. Yeah. And so now that we have allocated this, we change this to a 24, right? Then it's very long. Da-da-da-da-da-da-da-da. Then we free P3, so that 24 should change to a 25. Yes. Then we free P1, which should not modify anything other than this 1C to a 1D. Yes. And of course, like now it has a left child, which should be the new guy that just entered the red-black tree. And then after that, we free P2, which should trigger a huge coalesce that would make 1D go back to the original huge number, which, if I remember correctly, was 7D. Yes! Perfect. And so now once we free 7D, we should be free to do whatever we want, because it's all in. Now, my only question is, why did this change, right? Because this is not supposed to change. The size of those blocks is not something we're concerned with. Because when we run coalesce, right, when we run, let me find it. We run coalesce blocks. We take the new size and we just set the size for that, and we do absolutely nothing else. So why are we setting those things down there? There's only one block and one block only. So why did we set this to FFF? Let's see. We first remove the next block from the red-black tree. So we coalesce the blocks together, and then we try to see if the previous block is free. If it is, we remove it from the red-black tree, then we coalesce the blocks. Then we reinsert it into the red-black tree, which changes all of these flags, yes, but it should not be changing these. Nonetheless, we are indeed left with the correct state for a red-black tree. So this is correct, if I'm seeing it the right way. Which is very nice. I mean, we should be happy, because like this means the red-black tree is actually working. This means that free is actually also working. Yeah, I think we're in the right? Like, I don't see any mistakes. It went back to 7D, which is the total size of the free area that's available. It is correct. It has no left child, no right child. It has one parent, which is the ghost node. And the 1 indicates that it's black because it's the root of the tree. I think so. Are we witnessing a correct free implementation? I'm not sure. But I think this provides sort of enough confidence for us to start investing some time in making some automated tests. And then we return, right? There is nonetheless like one doubt that I have, like, why did it set those values? Because currently, okay, we go through the entire exercise, right? Then we set all of these things in the teacher, right? Then we free P5. Great. So now this is where I want to start looking. Let's add a new view that says, well, 0x1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 5, F17, C0. Perfect. And so now we allocate P1, P2, and then P3 should change. Well, it should actually not change anything. P3 should just make that a 24. Yes. So now we free P3, which should make it a 25. It should free P1, which should make it a 1D. Yes, and then it changed, the left child of this guy. So for the right child of that guy. And then it changes these values. Oh, wait, no, I'm stupid. Of course. Oh my God. Okay. No, those values need to change, and we should be scared if they don't. The reason is, P3 is the first one to be inserted into the red-black tree, right? So P3 enters the red-black tree, and P3 has a total of 24, right? After the alignment. So 12 plus the 16, right? Sorry, 12 is like smaller than 16, so its size gets converted to 16. And then 16 plus 4 is 20, which is not enough, right? It should be 8 bytes aligned. And so it becomes 24 in total. The problem is the block was size 28. So to accommodate for a... Actually, sorry. We want an allocation of size 20, right? No, guys. Okay, I'm getting confused. Wait. I'm so sorry if I'm confusing you too. So we try to allocate 12. That gets converted into 16 because the minimum is 16. Then we try to look for a block that can accommodate for our request. The only block that's available is a block of size 28. The problem is 28 minus 16 leaves us with something that's smaller than 16, which means that if we were to partition that block, if we were to cut it, partition it, to leave a free part out, we would be left with a free part that's smaller than 16, so it cannot be a free block, and thus we just give to it the entire block. So P3 is actually occupying, despite it being 12 bytes, a block of size 28. So P3 is the first one to be inserted, and it has size 28. Right? Let me... P3 is the first one to be inserted, and it has size 28, right? Oh, okay. Oh, 28. There you go. Perfect. That's P3. Then we free P1. So P1 now gets inserted into the red-black tree of 3 blocks. Monte Carlo simulations. Thank you for following. Yay! A new follower. Yay. Okay. We're growing, guys. We're growing. We have like 86 followers now. Which is absolutely insane. 1 week ago we had 12. Something like that. But yeah, so we have this guy, right, which is 28. Then we free P1, which P1 wanted an allocation of 24. And it actually got a block of size 1C, if I remember correctly. So 1C is in hex, also 28, right? 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 I think so. Actually, no, I think I have it. I have everything wrong. I have everything wrong. Let's just go. Let's just try it out. Let's just try it out. Do not trust my word. Doing this in your head is always the way to get bugs. So let's see. Okay, P1. Perfect. Let's delete this memory view and go to where the heap is now, which is this guy. So 0x 1, 2, 3, 4, 5, 6, 7, 1, 0, 0, 5D57, C0. Perfect. Okay. So everything is free. Now block 1, P1, gets a block of size 16 plus 12. It should be 28. So P1 has size 28. Let me just write them down. P1 has size 28. Then P2 gets a block of size 34. And 34 in hex is 48 plus 4, 52. Okay, so now P2 has a block of size 52. And finally, we have P3, which gets a block of size, let's see, so P3 would be this guy. It's over here. P3 has a block of size 24, which is 2 times 32, and 32 plus 4, 36, which is a little bit confusing. Why are we giving it a block of size 36? So 36, its minimum requirement is to have... Yeah, okay. So for a block to be partitioned, it needs to have a size of at least 40, because the whole metadata, like an entire block, the whole metadata occupies 20 bytes. 20, which is 4 bytes for the size and then the 16 from the user section. So in total, 20. So we cannot partition this block because it's 36 long. So instead, we just give the entire thing to the user. Okay. With that said, now we can reason about it. So first we insert P3, which has size 36. So we free him. And it is the first node in a red-black tree, so it's going to be black. Right? Then after that, and let's verify that the console is actually saying the same thing. So P3 should now have, black as its color. Perfect. After that, we insert P1. So P1 is smaller than 36, and we insert it as a red node. So now it should be 28. And nothing has changed. That's the way things should be. So now let's see what happens. Now P1, where is P1? P1 is here, 1D. Size 28, yes. And its parent should be, 70. It has the zero, the least significant bit set to 0, which is red. And thus we're also fine with that, which is perfect. 36, 28. And then after that, we try to insert P2. And P2 has size 52. And things shouldn't change at all, right? Because when we insert 52, we just insert it to the right of this guy, and we make it red colored. 52, right? We nonetheless have to have in mind that... Oh, wait, no. When we free P1, that's the state of the tree. And then when we free P2, we actually remove both of these from the red-black tree, merge them together with P2, and then we have a single red-black tree that is of size whatever the sum of them all is. I think if I remember correctly, it's like 106, the total space we have. alignment sort of changes things around. But after P2, interesting. So then we do have a right to be bogged out. Because if we remove those elements from the red-black tree, both P3, which lives here, and P1, which lives over here, we shouldn't be setting the metadata that they have. P1 lives to our left, right? P3 lives to our right. We first get rid of P3, if I remember correctly. So, what's going on? The next block to us, so let me just enter the function for P2. Yeah. So P2, it should detect which block it is, which is block 56. It asserts that it's indeed not free, sets the size, and says that it's free. Now we calculate the next block, which should be this guy over here, should be him, right? And so after that, and in fact, we can verify that by saying men heap low plus the 112. And it should, error. Sorry, men heap low returns a void pointer. So first we'll convert it to a char. Perfect. It should be address that where the 27 lives. Yes. So this points to P3. Now we know that P3 is not a no-heap pointer, and it's also free. So we should be able to enter this. And when we remove it from the red-black tree, we shouldn't be seeing... Oh, okay, yeah. The removal from the red-black tree is the one that's setting all of these flags. Because, yeah, when we remove it, we inherit the error. I think it's over here, where we, before deleting it, we link its parent with null pointer. Yeah, okay. I think we are good. Because then we coalesce the blocks and everything continues fine. We also remove that block from the red-black tree and we change it and then we reinsert it into the tree. Perfect. Okay, never mind. I was just seeing ghosts, it seems. Okay. This means that the memory allocator is working actually, which is absolutely awesome. Of course, we haven't tested it like nearly as much as we should. That's what we are going to sort of do. Because now we need to think, what is a way to introduce automatic testing? And what I mean by automatic testing is like running, something that you're able to run, some sort of test that you're able to run, and check that every single byte of the heap is actually what it's supposed to be. So we need to develop all of that testing infrastructure, I suppose. The problem is like how to do that without recreating the entire memory allocator, right? Because like checking that every byte of the memory allocator is right implies you behaving as the memory allocator and being able to know where the bytes should be, which implies we would need to rewrite the memory allocator to test the memory allocator. If we want to test that it's doing and putting the bytes where they need to be, then we would need to recreate it, which is not feasible. Instead, we could test for behavior, like, did the heap expand? No, it didn't. Good. Like all of those things. Is there still a free block for me? Yes. So good, right? So testing the behavior rather than the exact byte placement. And yeah, so after that, I think we can be sure about it. And we also need to test the red-black tree implementation that we have, but in C, because remember that I think we have another. Let me see if I can open another window. File, new window. And then I'm gonna open data structures. Because data structures is the folder that holds our previous implementation of the red-black tree, the one we did in C++. This is where everything started. And this one we did test, right? We tested the left rotations, the right rotations, we tested insertion, we tested deletion, we tested find. So the thing is, what we did is we grabbed this exact same code for the red-black tree, and simply translated it to C. So instead of using this, we use just the word black because C doesn't have namespaces and all of that. We also cannot use the function link. It had to have a different name because there's already a function called link in C. Instead of color, we call this BK color, so we just changed the name. So the behavior is exactly the same. Allegedly, and that's sort of what bugs me, because what happens if we made a mistake during the translation and we just didn't notice? I don't think we made a mistake, but once again, that's what everyone says, right? Like, we. So I'm not sure if we should test this. I think we should, and you can take a look at the code, how it looks exactly the same, right? While true. If, and then compare them both, right? And then here, if the color of the current is black, then return. Ooh, hello, Stephen LB. Ooh, thank you for rating, yay. We have 3 people. Thank you very much, and good luck with the memory allocator. Thank you very much. And yeah, we actually have it seems like we finished. It seems like it, but we need to test to like actually make sure that it's correct. And yeah, thank you very much for joining. So as you can see, like the code is translated line by line, right? Set the color of the new node to black, right? Color of the new node to black, then break. If the color of the new node is different from red or the color, you get the point, right? So it is the exact same behavior, but maybe I did something that I was not supposed to do and that messed up everything, right? So that is concerning. It's a little bit of a existential crisis because, you cannot. Rule number one of programming is never trust your star. So, yeah, let's do that. I just don't want to live with the doubt of like, having forever be like, oh no, actually the red black tree implementation is incorrect, and we're being super inefficient in the allocations. Okay, so we have a red black tree header file. Yeah, we're gonna have a main. And what we're going to do is we're going to simply assert that, actually no, we can just run test, and we're just gonna translate these tests to, oh, I think we closed it. Well, Control N, I think? No. Control Shift N, there you go. Then this guy, we're gonna open data structures again, and take it here, and then increase the font size so that you guys can see. I think this is the correct font size. Yes. Perfect. So now we go to test red black tree, and then we just port these tests that we've been doing. We simply need a way to create nodes very easily. So let's start with test left rotation. So test left rotation, and then here we just call it test left rotation. Okay, perfect. And what we're going to do is we're going to create a bunch of nodes. I think now it is possible to do? Question mark? I think, ouch. Yeah, I think we're fine, right? Because what we can do is, I don't know what to do. How do we test it? We need, we need to, okay. Let's just write stuff and do something like create block, right? So we're gonna have a fake sort of arena, right? Fake arena, a fake arena, and then this thing's static. And in that arena, we're simply going to store like a big heap, something like, I don't know, it's 256 bytes, right? So that's our arena. And of course, we need to import, actually include the standard library. Perfect. So what we're gonna do is we're gonna implement a function to create a block. Right. We simply what? We simply keep track of h pointer t to, like, you know, next block, and then it's gonna be 0. So what we're going to do is to create a block, you would need to pass multiple things. So the size, right? And yeah, let's just do the size. And then all we need to do is we need to go to the arena, go to the offset of the next block that's free. And to this, we need to interpret it as a block header pointer. And then modify its size. Or actually, even better, bk set size. Set size to be, well, this doesn't have access to the heap, which is concerning. Yeah, I'm so sorry, guys. I'm all over the place today. It's not, I'm not really sure of, I think we can just do this and that'll help us. Yeah. So if we tell the library to use the heap that we pre-allocated so that it takes a look at, so that we can take a look at it. Yeah, and then we set the size of block number new block to that size, then we should be able to see what happens with everything. Yeah, so Yeah. We're fine. So let me just do one megabyte of, sorry, 1 kilobyte of memory. And then initialize it to 1024. Hello, Stinky Sandwich 12. welcome to the stream. Sorry, I've been all over the place because we're trying to test our memory allocator now that we have implemented most of the functions. And so what's going on now is we're trying to create like the testing infrastructure, right? Like a thing that allows us to check that everything is going correctly. It's just that I'm a little bit all over the place because doing that can be done in multiple ways. I'm trying to decide which one we want. I think we're landing on something because we can return this guy. Yeah, no. We're coding it in C, and there is not much of a need to have direct access to RAM. since of course like the operating system is going to provide you with memory pages, and you just ask for a memory page and so on and so on. So we can just implement it in C. Actually, it's C is the universal language, so should be no problem. Um, what's a memory allocator? Yeah, it basically is the one that allows you to, in the case of a programmer, right? Your program needs memory constantly. Maybe you create a variable or you create objects that you store in the heap. The memory allocator is just the guy that is in charge of managing all of that memory for you. So when you allocate something, it's the one that tells you, oh yeah, this block of memory is what you may want. And when you want to stop using something, you call free on that block. So the memory allocator is the one that says, oh, okay, now I know that this piece of memory is free. So when somebody asks me for more memory, maybe I can give them this block back, and so on and so on. So it's the sort of middleman between the programmer or the program itself and the amount of memory that's available to the program. Yeah. Um, and currently we're just trying to test it. It's just that seems a little bit difficult. I don't know. Yeah. Memory to them. It is a little bit different. It is different. When you set up a virtual machine, I mean, virtual machines are a little bit of a different beast. They use like hypervisors and etc. It's a more low level thing. A memory allocator is sort of more program specific. The reason it's like there is a difference between what you're suggesting, which would be more like a virtual memory pager, it seems to me, which is a more low level notion. Just the way the OS manages who to give memory to and like which pages go to who. A memory allocator is once you're able to get memory from the kernel, which answers coding Barra's question, yes, right? You then need to manage that memory somehow. Because the operating system does, if you want, say, 26 bytes, right? It doesn't give you the operating system doesn't just give you 26, it gives you like a whole page, for example. The memory allocator is the one in charge of saying, okay, we have all of this space. How do we manage the actual, how do we manage that space that we've been given? I might be wrong, but can't you just create a block of memory with your code, print it, try and modify it, then print it again and see if it's different? Yeah, so the thing is, if you modify it, then it's going to be different. So what we have right now is we have been seeing that the allocations do work, right? Like it seems that everything works and the information is indeed being stored where it's supposed to be stored. What we want now is to make it a little bit more automatic so that I can just run the tests and tell whether or not the program is behaving correctly instead of just inspecting the memory, seeing with my eyes, is everything there? Not only that, but you, through the program printing it, can see the sort of the information you stored, but the metadata, it's something you shouldn't be able to access, or at least, right? So we also need to check that the metadata is correct, that the size of the block is what it's supposed to be, that the red black tree is behaving correctly, that all of that is like functioning the way it's supposed to. Let's see. To be honest, as a game dev myself, this is super out of my league. I don't mess with low level stuff a lot. No. Because like that's the exact reason why I started these streams, right? I didn't know about memory allocators before starting. I did know, right? Like I had watched the lecture before starting the stream to know what we were actually going to do. But this is a project to learn about memory allocators and like how they work and what it's supposed to be. So yeah, it's completely open to beginners and ask any questions you want. Any ideas you have, completely accepted. Like just let me know, and then we'll evaluate that idea. Many good ideas have surfaced from many of the chatters that are present. Um, and so you're always encouraged to ask questions, to suggest something, etc. Coding Mara asks, how old are you, Sharif? I am 20. I'm 20 years old. I was born in 2006. So yes, still in college. Um, yeah, that answers your question. So yeah. Ah, okay, we need to figure this out. We need to figure this out because I want to at least have a clear picture on, like, how to um how to test this, because, like, the functions themselves, they change the size of stuff, right? So if I maybe pass it a block of size 16, then it's going to change the value to 20 because of the alignment. And so now I don't know where the next block is going to be unless I emulate the whole alignment process, which is kind of annoying. Um, Anyways, the chat. Bro, if you can do this while you're 20, you're gonna be insane later on. Yes, it's crazy. No, do not. You're putting too much trust on me, but yeah, I mean, not sure. Hopefully, we can all grow to be like super expert programmers or something like that. Um, yeah, hopefully, AI won't take my job. But thank you very much. Thank you very much for the compliment. Mm, yeah, I mean, you know what I'm thinking of? Because what I was thinking is, oh, we could just make use of heap pointers, right? And actually, I think we can just do that. No. So when we set the size of that block, we assume that's the header, and then after that, okay. So what we do is we're going to say, well, the next free block, it's going to be present at the size of whatever this guy is right now. Okay. Wait, yeah, what am I saying? Yeah. Wait. I said that the size is greater or equal to 16. Sorry guys, like I'm going to write some code and like make sure that it follows the idea I have and then explain what we're doing. And so we have an assert, then we set the size, then we have the block size for the new block. This actually is not that needed because we can simply make it be plus equal to size. So we plus equal, yeah, what? It doesn't count the 4 bytes. So then we just do this. Size of the U32T plus the size, and then we end up in the place we want to be in. Yeah, okay, so to insert a new block, we simply set its size, and then we say that the new block starts at whatever it means to skip this block. And then we return what the new block is. Yeah, so yeah, I'm really dumb. Not sure why I didn't catch that before. Heap pointer T, old new block, and that's exactly what we're going to return. Okay, so now in the left rotation, we can emulate this behavior where we say, well, 5, this block called 5 is just gonna be, create block of size 50, right? Okay, Create your own RAM by soldering every module by hand. True. First time chat. Eid ein Bihat. Welcome to the chat. Yo, mind if I share something I've been building? Need some feedback. Sure, man. I mean, you can just paste it in the chat and we can take a look at it. We have 15 minutes left of stream, so yeah. But can't you just like create like 4 GB of virtual RAM with page files, then run on its own operations and read, then check if it's supposed to be like that? Yes. Yes. And that is sort of what we're trying to do. Yeah, basically that's what we were trying to do. So we're just running the code to do that automatically. Once we have allocated all of that, with the memory allocator, we let it run. And then as it goes through every step, every alloc, every free and all of that, we check whether or not the state is correct. But yes, what you're saying is the right thing. Or at least the right idea. Currently, we are instead testing our red-black tree just because I'm paranoid that I didn't translate this correctly. So yeah, let's separate like 1 megabyte of space. Heap size 1 megabyte. So we're just gonna have 1 megabyte given from the operating system or whatever. For now, we'll just use the normal malloc to do that, just because it's easier to do. Heap size, and here we have heap size. Perfect. And then here, we do 5. Oh wait, Gogo04, thank you for following, and same for MattFlash19. Yo. Funk main create blog 026 reblog, etc. I was just making up stuff since I don't know your code. Yeah. We're going to do something like that, right? Because currently we're just trying to get an interface similar to the tests we had before, where we create a node object. Here I'm just creating like the objects again. So 2 is equal to create block. This is gonna be 20. HTRT 10. This is gonna be create block 100, and then another heap pointer for 8, which is equal to create block of 80 actually. Then the heap pointer for 12 should be equal to create a new block, which is 120 long, and the heap pointer for 6 should be equal to create block of 60. And then finally, we have a heap pointer of 9 is equal to create block of 90. I multiply them by 10 because the memory allocator rounds very small numbers to, to like the next multiple of 8 and whatnot. Currently, we're not using the memory allocator, so it's gonna be, it's gonna be loyal to these sizes. But remember that the minimum size we can have is 20, so that's why I'm doing it like this. Perfect. So we have these things, these little guys, and then what we do is we link them together. So I think we call, I'm not sure if we can do this, but we call t-link on 5 and 2 true. Oh, it works. Okay. So basically we're constructing the red-black tree that we want. And I think we can just copy these function calls and just add the t at the beginning and change all these ampersands to be nothing. Perfect. Awesome. And so now, what we're going to end up doing is we're going to have, at this point, a red-black tree. So what is going on? What's going on is if we take a look at the design, we're grabbing the node 5, right? Sorry. We're grabbing the node 5, and then we're linking it with 2 on the left. Then we're grabbing 5 and linking with 10 on the right. Then we're looking at 10, and then we're linking it with 8 on the left, right? And so on and so on and so on. So we're basically creating a tree, and then we're going to perform rotations on it, which is why you see this guy, right? So another heap pointer called res. Then we're going to left rotate the tree. At which node? Well, we're going to rotate it at node 5. And we expect the answer to be a different tree, right? And so this is where things get a little more complicated, I suppose. Because what we're going to store is an int array. It should be something like the expected tree that we get, and we simply make this be the pre-order traversal of that tree. So we expect the tree to now look like 10, 5, 2, 8, 6, 9, 12. Right. I'm not sure how you make the arrays in C, something like this, yeah. And now we also need another array called sort of like result or something like that. Or yeah, I assume vec3 is a better name. And it has space for, say, I don't know how many integers. 1, 2, 3, 4, 5, 6, 7 integers, which is the amount of nodes we have. And what we need to do is we need to convert sort of the red-black tree. Because remember, currently res holds the pointer to the root. And so now we need to put that tree and like make it an actual sort of pre-order traversal representation of what the tree is. And so we should do something like arbitrary to vec, and then pass it res and then the vec tree, which is exactly this function that we have here, arbitrary to vector. I think we can, if it is helpful, just export it as like debugging, but actually I think we can just write it. I think it would be useful here, yeah. So debugging, just if people want to print the tree somewhere, we can just have a void arbitrary to vec, and then that arbitrary to vec is going to accept a heap pointer to some sort of block, and it's also going to accept a array, which we call result, right? What are we going to do? Well, we're going to, inside result, which I guess I prefer to pass as a pointer. Inside result, what we're going to do is say, well, if the heap pointer that you passed to me is a null heap pointer, it means that I simply need to return. There's nothing else I need to do here. Otherwise, to result, we add the pre-order traversal, which should be the results value is equal to my block size. So bk size, and then I enter my block size. And then I call, oh, what's going on? Result expression, result unused. Oh, okay. And then I call the same function, but now on whoever my left child is, bk left, for this block, and for whoever my right child is, bk right, in this block. Perfect. Oh, and of course, we pass to it result plus 1, since we already included the information of the root. And oh, we're gonna have a little bit of a problem. I think we're gonna have to return a number here to keep track of which position of the array we're in. Return 0, like I added 0 elements. Then result should be equal to this. And then, yeah, and then what we do is we return the amount of elements that were added by going to the left branch plus, so here it would be 1, which is the one I added, plus the amount of elements that were added by the left subtree, and then that plus whatever this is. So I think I'm gonna have to in32t left elements. It's gonna be this much, and then we have right elements. So the reason why I need to do this is because, you know, the right subtree needs to know in which part of the array does it start including the information. So the left subtree knows that from the start of the array, the root is written in the first position. So then it's just going to start writing from the start of the array plus 1. But the right subtree doesn't really know where to start, because the left subtree could have added 3 elements, 2 elements, 1 element, 0. We don't know. And so that's why I'm making them return the amount of elements they added. So now what the right tree does is, okay, please convert to vector my right subtree, and then start at position result plus 1, which is the root, plus the amount of elements added by the left, right? That should be completely fine. And then after that, we return the amount of elements we ourselves added. We added 1 plus the number of left elements we added, plus the number of right elements we added. Perfect. That should be fine. And that should be able to convert an entire red-black tree made out of blocks into a single array that contains their pre-ordered traversal. Call to undeclared. Oh yeah, of course. So now inside this red-black tree, this implementation should not go here. It should go somewhere. So I think if I just copy the entire function, it will be fine. And then I just modify this to support the signature. Extern, then in regular tree C, Here we go to the debugging section, debugging, and over here we paste. Perfect. Okay, I think that solves all of our issues. Yeah. Okay, perfect. And so the only thing we need to do now is compare the two arrays, right? So we assert that they have the same size, but we cannot really assert that. We just know that this guy has size 7, and we simply initialize everything in it to 0. And what we're going to do is, yeah, we're just going to iterate through the entire thing. So I smaller than 7, which is the amount of nodes, right? 7, and then plus was I. And then what we do is we simply check, we assert every time that vectree's position I is the same as the expected position, right? And after that, if nothing happens, then we say, yes, the test passed, and we return true. So I think this is performing the sort of same work that the previous piece of code was doing, which means we can test our left rotation. As a final, because it's 9:58 already, which means I have to go, because I have to go at 10 a.m. But as the final sort of moment in the stream, we can see if this worked. So I don't want to test test, I want to test arbitrary test. Let's see. And then this should be saved as arbitrary test. Perfect. So now we can run it. Let me modify this launch JSON to say that I want to run the arbitrary test instead. So let's run it. Let's see what happens. Let me introduce a breakpoint over here. F5. Okay. Heap size is equal to hopefully, 1 megabyte. Yeah. Perfect. We malloc whatever that is. And then we continue. We test the left rotation. Perfect. So 5, and I guess one of the things I do want to do is take a look at this in the memory inspector to see that we're doing the right thing. We add a new view, and then we say 0x 1 2 3 4 5 6 7 9c d 4 1 2 3 4 5. Okay, that should be it. We put in 5. No, guys. Okay, so this is asking me a modulo 4. That's so annoying. It's okay. I think if we can just comment it out for now. Just remember to change it after we finish this. Okay. Okay, 5. So now we need to change the memory inspector since the address changed. It's changed to 0x 1 2 3 4 5 6 7 A0A 8 1 2 3 4 5. Perfect. Okay. Now we look at 5. And 5 when it's created. Okay, perfect. 32. 32 is, let's see, 50 in hex. Yes. 50, then another block should be created right next to it. Yeah, 14. Well, actually, that's not quite correct. It doesn't really matter. Yeah, we create all of the blocks. Okay. Now we link 5 and 2. 5 and 2 we link together. And yes, it points at block 36. Then we continue. Da-da-da-da. Oh, no. That's okay. Okay. I think we're gonna leave it here because I have to go now. I'll keep thinking about this and how we can actually do this, because currently the testing infrastructure is not that strong. But yeah, I do have to go now since it's 10 a.m. But it was a pleasure today, guys. So, I think we have finished. I think we have finished. I don't want to ruin it. Like maybe, when you say something's correct and all of that, and then it ends up being not correct, and then after you test it and everything. So I don't want to give the bad luck, but I think our implementation may be correct from the little tests we made before. Tune in tomorrow to see if that's the case, because we're gonna finish this whole thing and have automatic tests. And yeah, thank you everybody. Let's rate AK elements. That's true. I've never rated anybody, to be completely honest. So maybe we should do that. Maybe we should return the favor. Because I remember Jasper joined at some point in time. So how do I rate somebody? So I go to twitch.tv and then what do I do? So do I go to that person's, let's see, AK elements. So this person, wait, let's see. Is this a stream we would be interested in rating? Like what are they doing? Let's see. Adding slang shader language to the engine. Oh, we have some ads. Sorry about that. Oh, please. Let's wait. In the meantime, how do I rate somebody? So do I report? Ooh. What is this language? Oh, wait, no. This is. Is this C++? Yeah, wait, no. It looks like C++. Yeah, no, it is C++. Yo, great. Uh, yo, if you guys are interested in the stream, you should definitely join. What is the, let's see, slang shader language to the engine? Um, Chef's Almighty. Chef's Almighty. What is Chef's Almighty? Let's see. Learning C. Yo. Okay, I think we can join that one. Uh, let's wait. Let's wait for it to load. Yo, they're learning C. It says over here. So I think this is more, it's more akin to what we've been used to. C, and then this person is learning. So I think we can go here. Yo, okay. How do we do it? I think maybe in the stream manager, creator dashboard. Now you're gonna see all of my stream account. If I go to stream manager, wait for it to load. Yo, wait, what is this project? No, I'm curious. Wait, how do I? Let's see. In the console, how do we raid somebody? Do you guys know? Is it slash raid and then channel? Oh, in my chat, use slash raid. So if I just do slash raid and then the channel, so do I say Chef's Almighty? Is that the way? If so, when I click enter, I think we're gonna go to that stream. So thank you everyone for hanging around. Hope to see you tomorrow. Remember, streams always start at 7:15 and end at 10 a.m. So yeah, be ready, be ready. It's a schedule, and hopefully we'll be able to rate this other person that are learning C. Okay, bye bye. Whee! Let's see. Ah, Sheep's Almighty's rate settings do not allow you to rate at this time. Oh no. So what do we do? What do we do? Oh no. Maybe the C++ guy. Yeah, so AK what is his name? AK, where is AK? I forget the name. AK Elements. AK Elements. Let's go to AK Elements. AK Elements, it's live. Okay, perfect. So we can, let's see, slash raid AK Elements. I think that's the name. Yes. What is he doing? This is very intriguing. Okay. Gonna leave you guys um with with AK Elements. Let's take a look at his stream. All right. Bye bye. Let's see. Ah, dude, come on. Dude, rate settings, AK Elements rate settings do not allow you to rate at this time. Okay, it seems like we're unable to rate people. I'm not sure they have disabled it or something. Yeah, given these two creators, you guys should migrate to either of the two, and yeah. So, oh, last attempt. Wait, give me a second. Oh shoot, no. Oh no, wait. Okay. Christoph IT Zig guy. Okay, let's see. Christoph IT. Ooh, he has 73 viewers. What is? Wait. Okay. I think maybe most of you may be interested in his stream. So I think. Wait. Okay. I've. I don't have much time to wait for the ads. I would like to see this stream. I do have to go now. So let's do raid Christoph IT. All right. No, it says that his raid settings don't allow me to raid at this time. That's unfortunate. Yeah, it was the last attempt. I do have to go now, but check out those creators. Take a look at them and see if maybe you like what they're doing. But yeah, okay, all right, guys. We'll see you. We'll see you tomorrow. Gotta go now. Okay, bye bye.